What if I told you we've already touched the edge of room temperature superconductivity? Not in science fiction, in peer-reviewed experiments. In 2020, researchers reported a hydrogen-rich material that became superconducting around 260 Kelvin, about 13 degrees below the freezing point of water. That's not liquid nitrogen cold. It's not near absolute zero. It's freezer cold. So yes, by temperature alone, we're shockingly close. But here's the real story nobody tells you. The problem isn't those last 13 degrees. The problem is the pressure. To get that performance, the material had to be squeezed under pressures so extreme they only exist naturally deep inside planets. Pressures we can typically sustain only in tiny samples using diamond anvil cells. So the real holy grail isn't room temperature. It's room temperature at ambient pressure. Superconductivity you can use in a cable, a magnet, a motor, a device that lives in the real world. And that's why this field feels like a paradox. In the lab, the physics works beautifully in engineering reality. The material doesn't want to exist. If you remember, LK99, the 2023 claim that went viral and collapsed, this episode will also show you why superconductivity is so easy to misread and what counts as proof. Because if we ever solve ambient pressure near room temperature superconductivity, it won't just be a better material, it will be a different civilization. Superconductors matter because resistance is everywhere. Every time current flows through normal metals, some energy becomes heat. That heat is waste in power transmission, a design constraint in motors, and a scaling barrier in high-field magnets. A practical room temperature superconductor, meaning ambient pressure and near room temperature, would be disruptive across a few core areas: power and grids, lower losses and new ways to route large currents, especially in densities where space and heat matter. Magnets, MRIs, scientific instruments, particle accelerators. Today, many rely on superconductors that need cryogenics. Room temperature superconductors will reduce cooling complexity dramatically. Transportation and industry, lighter, more efficient motors, improve high power systems, potentially new architectures for generators and industrial equipment. And yes, fusion magnets are part of the discussion too. But even there, superconductors don't magically create energy. They reduce complexity and improve feasibility. The key is this: superconductors are not a gadget upgrade. They're an infrastructure material. But the only superconductors we can routinely use today either require deep cooling, or they come with manufacturing and brittleness limits. So when you hear we're close, you need to ask, close in temperature or close in engineering reality? Those are very different distances. Let's anchor this in the most important modern result: hydrogen-rich superconductors under high pressure. In 2020, a team led by Mikhail Aramets reported superconductivity in lanthanum hydride, commonly discussed as LiH, at around 260 K under extreme pressure. And what made this result matter wasn't just the headline temperature. It was the quality of the evidence. Multiple measurements consistent with superconductivity, and follow-up work from other groups exploring similar high-pressure hydride systems. This is the kind of result that convinces scientists the physics is real. Not just a resistance drop, but consistent behavior in magnetic response and thermodynamic signatures. So the field learned something crucial. Room temperature range superconductivity is not forbidden by physics, but it may be conditionally allowed only when matter is forced into extreme structures by extreme pressure. And that's the tension that drives the whole story. If pressure is a mechanism, how do you ever remove it? Superconductivity isn't very low resistance. It's a different state of matter. In ordinary conductors, electrons scatter. Scattering becomes heat. That's resistance. In a superconductor below its critical temperature, electrons form Cooper pairs and move through the lattice without the usual scattering that creates resistance. That gives you the first signature, zero DC resistance. But that alone isn't enough to convince serious scientists, because measurement artifacts exist. The second signature is magnetic. The Meissner effect, where a superconductor expels magnetic fields in a characteristic way. That's why genuine superconductivity is not just a better wire. It's also a fundamentally different magnetic material. This matters because it gives you a Credibility test. When someone claims superconductivity, the hard questions are, did they show true zero resistance in a robust measurement? Did they demonstrate the right magnetic behavior? Is it reproducible? Does theory support the observed mechanism? Keep those questions in your pocket. They're how you avoid getting fooled by the next viral claim. Now, why do hydrides get so hot in the first place? Here's the key mechanism for many high-pressure hydrides. Electron-phonon coupling. Phonons are vibrations in a crystal lattice. In many conventional superconductors, phonons provide the interaction that lets electrons pair up. Hydrogen is special because it's extremely light. Light atoms vibrate fast. Fast vibrations can raise the energy scale of pairing. Under extreme pressure, hydrogen-rich materials can form dense structures where phonon frequencies are high electron. Phonon coupling becomes strong, and the predicted critical temperature rises dramatically. In simple terms, pressure forces the atoms close enough and stiff enough that the pairing interaction becomes unusually effective. But that creates the trap. Release the pressure and the structure changes. The lattice expands. The vibrational spectrum shifts. The conditions that enabled high TC weaken or vanish. Sometimes the phase you created under pressure isn't just less superconducting at low pressure. It's not stable at all. So the question becomes, how do you get pressure-like conditions without an actual diamond anvil cell? That's where the field strategy turns from discovery to design. Now let's talk about LK99 briefly and usefully. In 2023, LK99 was claimed as a room temperature, ambient pressure superconductor. It went viral because it offered everything the world wanted in one sentence. But the scientific community did what it always does with high-impact claims. It tried to replicate them, and replication failed. The consensus moved toward not a superconductor, with observed behaviors better explained by more ordinary effects, including issues like impurities and misleading magnetic responses. This isn't a story about evil or fraud. It's a story about how easy it is to confuse a resistance animalia phase transitioner, a weak magnetic effect, with true superconductivity. And that's why the hydride results matter so much. They come with a clearer theoretical framework and a more consistent evidence chain. LK99 taught the public hype cycle. Hydrides taught the field what real progress looks like. Now we return to the real wall, ambient pressure. If you want a single sentence for the whole episode, it's this: temperature isn't the only target. Stability is. A room temperature superconductor isn't useful if it only exists at microscopic scale under hundreds of gigapascals inside a diamond cell for short experimental windows. To be an engineering material, it needs to be stable at normal pressure, manufacturable in bulk, formable into wires or tapes, mechanically robust and able to carry high currents in magnetic fields. That's a brutal checklist. It's why even today's commercial superconductors are hard to deploy. So when people say we're close, the honest response is we're close in temperature under extreme conditions. We're not yet close in deployability. And that distinction is what separates a lab record from a civilization upgrade. So what are scientists actually trying? Not one more degree. They're trying to eliminate the pressure requirement. The last 13 degrees isn't the canyon. The canyon is a pressure drop from extreme conditions to 1 atmosphere. Right now, no confirmed hydride gives you near-room temperature superconductivity at ambient pressure. And within phonon-mediated frameworks, it's plausible that high TC relies on structural states that only exist under compression. So the field explores multiple paths. Chemical precompression. Using chemistry to mimic the effect of pressure by packing hydrogen densely inside a stable lattice at lower external pressure. More complex compositions. Ternary and higher-order hydrides, where structure and bonding might stabilize high DC phases at lower pressures. New mechanisms. Beyond simple phonon-mediated superconductivity, because the best ambient pressure superconductors we have, like cup rates, involve physics that is still not fully settled. This is where the emotional tension becomes real. We know room temperature superconductivity is physically possible in some regime. We don't know if the practical version, ambient pressure manufacturable, exists in nature's rule set. That's not pessimism. It's an honest boundary between known and unknown. If someone cracks ambient pressure near room temperature superconductivity, the impact is huge, but it won't be instant magic. It would first reshape places where superconductors already matter. High field magnets, simpler cooling, cheaper operation, new system designs, grid and industrial power, less waste heat, new high current architectures, transportation and motors, efficiency gains and design shifts medical access, more MRI deployment if magnet systems become simpler and cheaper research and manufacturing, a new baseline for high current precision tools. The important point: A room temperature superconductor doesn't create energy. It reduces friction in the electrical world. And removing friction changes economics. That's why this field keeps pulling talent and funding even when progress is slow. Here are the real attempts, framed soberly. 1. New hydride families and multi-element compounds. Theory-guided searches for structures that keep hydrogen dense without such extreme pressure. 2. Computation and machine learning for materials discovery, using models to scan huge chemical spaces, because humans can't intuition their way through millions of candidates. 3. Stabilization strategies, looking for metastable phases that can persist at lower pressure if formed under pressure, then quenched. Hard, but not impossible in principle. 4. Speculative control methods. Ideas like light-driven or non-equilibrium enhancement exist in the literature, but these are not yet engineering solutions. They're exploratory physics. This is what frontier material science looks like, not one straight path, but a portfolio of bets. In the next 5 years, expect more mapping, which hydrides work, what pressures, what mechanisms, and where the theoretical limits are. In 10 years, we'll likely have clearer answers on whether phonon-mediated routes can ever reach ambient pressure, or whether the field must rely on other mechanisms. In 20 years, 2 outcomes are realistic. We achieve a major step down in pressure for high DC superconductivity and unlock niche industrial uses, or we learn that ambient pressure room temperature superconductivity is extraordinarily rare or unattainable, and the focus shifts to making cold superconductors easier and cheaper to deploy. Either way, this field will reshape technology, because even partial wins matter. Cheaper cooling, better materials, better magnets, better infrastructure. Here's what to remember. We are not 13 degrees away. We are an entire engineering reality away. Ambient pressure, stability, manufacturability. LiH-class hydrides prove something historic. Near room temperature superconductivity can exist in the laws of physics. LK99 proves something equally important. Viral excitement is not evidence, and superconductivity is easy to misread. So the next time a claim explodes across the internet, you'll know the real test: zero resistance and correct magnetic behavior, independent replication, and a mechanism that survives serious scrutiny. That's how the future actually gets built. If you want the next episode, we'll go into the best ambient pressure superconductors we really have today, why they're stuck where they are, and what it would take to break through. Subscribe to Future Forge Explored, where we don't just chase headlines. We explain the materials frontier before it becomes normal. And trust me, you're going to want to see what comes next.